In this video, we're going to continue talking about the concepts of Chapter 5. Now we're going to focus on oxidation and reductions in organic chemistry and balancing chemical reactions. When it comes to oxidation and reduction in organic chemistry, we do not have to assign the oxidation number of the atoms in these structures. What we're going to pay attention is to the functional groups that are created when these chemical reactions happen. By definition, oxidation reactions in organic chemistry are going to result in an increase in the number of carbon-oxygen bonds by the addition of oxygen or the loss of hydrogen atoms. Reduction reactions are going to reduce the number of bonds between carbon and oxygen atoms. The slide in the bottom has structures and the different functional groups that are going to be interconverted in these reactions. But in order to have a better list and for us to understand what gets oxidized, what gets reduced, and what is the interconversion of the different functional groups, I'm going to just list the reactions that you are concerned with in a different page. So let's understand oxidation reduction in detail. So when we are looking at oxidation, versus reduction in organic chemistry, it is important to know what is the functional groups that I will be paying attention to. For oxidations, I'm either going to start with alcohols or an aldehyde. Please review how these functional groups look so you will be able to identify them in reactions. When it comes to an alcohol, let's understand that alcohols can be categorized into primary alcohols, secondary alcohols, or tertiary alcohols. A primary alcohol is going to be one molecule in which the carbon that is holding the OH is connected to one carbon chain. When it comes to a secondary alcohol, the carbon that is connected to the OH is connected to two carbon chains. When I have a tertiary alcohol, the carbon that is holding the OH is connected to 1, 2, 3 different carbon chains. If we look at oxidations of alcohols, primary alcohols will result in the formation of an aldehyde. Primary alcohols can also result in the formation of a carboxylic acid. Secondary alcohols are going to result in the formation of a ketone. And if I have a tertiary alcohol, understand that no reaction will happen. When we compare these structures of an aldehyde, a primary alcohol, a secondary alcohol, or a tertiary alcohol, the reason why a tertiary alcohol cannot get oxidized is because the carbon that is holding the OH does not have directly attached to it a hydrogen. And in the case of a primary alcohol, an aldehyde or a secondary alcohol, those atoms, that carbon that is holding the OH, it has a hydrogen atom. You can observe it here for the secondary alcohol. Here, the primary alcohol has 2. In the case of the aldehyde, we don't have an OH, but that carbonyl is connected to 1 hydrogen. So that's why these oxidations can occur. If we start with an aldehyde, the aldehyde has only 1 functional group to make. An aldehyde transforms to a carboxylic acid in order to form product. Now, let's discuss the reduction reactions. For reduction reactions, you will be concerned with only 2 types of reduction reactions. The first is when I start with an aldehyde, what is the functional group that I make? Versus when I start with a ketone, what is the functional group that I make? So if you start with an aldehyde and you end up with a primary alcohol, that is called a reduction. If you start with a ketone, ketones always result in the formation of a secondary alcohol. And this is the summary of all the reactions that you observe in this figure. Understand that even though it is illustrated that carboxylic acids can reduce to aldehydes, you guys are not responsible for that transformation. Let's now proceed to talk about balancing equations. One of the things that we have talked throughout chapter 5 is the idea of reactions. And when it comes to reactions, so far we haven't explained in detail how reactions work in terms of the number of atoms that may be present in these reactions. So when we have a reaction, it doesn't matter if it's organic or if it's inorganic, it is important that the reaction is balanced. Balance in a chemical reaction means that no atoms are lost or gained in the process of those reactants converted to products. And that is true because when a chemical reaction happens, the law of conservation of mass needs to be respected. This law actually indicates that in an ordinary chemical reaction, matter cannot be created or destroyed, meaning matter cannot come from thin air and be destroyed into thin air. There's going to be no change in the total mass of the atoms from the reactants and the atoms in the product. So in an ideal world, all the atoms that you start with, you're going to have them show up in the product. Now, this means that overall in a perfect system, if you take the mass of the products, it's going to be equal to the mass of the reactants. In the image that we have here, we can observe that this is representing a chemical reaction in which solid silver reacts with solid sulfur to make specifically solid silver sulfide. You can see that before some of the atoms, there are digits, okay? And that's to take into account that we have the same number of atoms in the reactants and the products. And we're going to practice in a few minutes how to actually place those digits in a chemical reaction. But overall, what I want you to appreciate is that if you start with a mass of a particular reagent, in this case, you can see that this is how much silver was measured out. This is how much sulfur was measured out. If you add this number plus this number, that's exactly what that equals to for the product that was made. When it comes to writing balanced chemical reactions, let's understand that there's some guidelines that need to be followed in order to write a balanced chemical reaction. In most of the reactions that we're going to be dealing with in this class, at least for inorganic chemistry and some organic chemistry, are always going to be balanced. It's just that in organic chemistry, sometimes we don't write in water or other atoms, but in the best of my ability, I will make sure that both inorganic and organic reactions look balanced for the purposes of this class. So you can see that in these guidelines, it's just telling you that you need to list the elements in the reactants and in the products. You need to count each of them. And you can only balance reactions by adding a large number in front of compounds or elements. You must not change the subscripts, because if you change the subscripts, you're going to change the identity of a particular compound. Let's practice with some problems to actually see how we balance reactions. And my major advice will be that when you're balancing reactions, the best thing that you can do is just practice, practice, practice. So here we have some chemical reactions that have been given in words, and we need to balance them. Let's go over the first one. It says solid potassium oxide. So if it's potassium oxide, this is K2O in solid form, plus liquid water, H2O, liquid, is going to form solid potassium hydroxide. Potassium hydroxide is KOH. And this is the basic chemical reaction. Now we have to count the atoms on the reactants in the products in order to know if they are equal or they are not equal. So I know that in this reaction, for the reactants, which I'm going to label with a capital R, we have potassium, oxygen, and hydrogen. And in the products, we also have those atoms, because remember that in a chemical reaction, the atoms cannot be destroyed or go into nothingness. So the same atoms that we have in the reactants, we will have in the products. When we do our count, we can observe that we have 2 potassiums, we have 2 oxygens, one here and one here. And we have 2 hydrogens because of the subscripts. When we look at the product, we only have 1 potassium, 1 oxygen, and 1 hydrogen. To balance this reaction, all we have to do is to put a coefficient in front of the KOH, specifically a coefficient of 2. Because placing that 2 over there, what that's going to do is that now that 2 gets multiplied by the subscript on potassium. So that means that my potassiums will go to 2. That's going to be multiplied by the subscript of oxygen. So that means that my oxygen is going to go also to 2. And lastly, that 2 gets multiplied by the subscript of hydrogen. So that means that my hydrogen will also go to 2. And now we see that we have 2 atoms of potassium, oxygen, and hydrogen, both in the reactants and the products. As you saw, we didn't put digits in front of the K2O and the H2O, but there's actually coefficients there. The coefficients that they get is a value of 1. So when no coefficients are added, that means that a value of 1 is there. Let's do example number 2 together and make sure that you practice at home 3 and 4. So for number 2, it says solid aluminum. So we say Al, S, and then we have oxygen gas. It is important that you know that when you have a chemical reaction, your diatomic molecules will be in the form of their diatomic elemental form for our reactions to occur. So when you see oxygen gas, this refers to O2. Next, we have as a product solid aluminum oxide. The chemical formula of aluminum oxide is Al2O3, and this is in solid form. Let me incorporate the states of matter of the other atoms that we have in this reaction. Next, let's actually do the count of atoms that we have for this reaction. I have reactant, I have product. Here I'm only dealing with aluminum and oxygen. So in the reactant, I only have 1 aluminum. When it comes to the oxygen, I have 2 oxygens. When it comes to the product, I have 2 aluminums and 3 oxygens. So we can see that in this second problem, the aluminums are not balanced, the oxygens are not balanced. So when we're trying to balance this reaction, we can say, okay, if I put a digit of 2 in front of the aluminum, that means that the aluminum will now have 2 atoms, so now it looks balanced. But when I move to looking at the oxygen, the issue is overall that oxygen, I have 2 in the reactants and 3 in the products. Many times, not all the time, but many times, especially if we have oxygens in the system, we want those to be even. It depends on the problem, but at least in this one, it requires it. And in order to do that, the common number that a value of 2 and a value of 3 have is actually the value of 6, because 6 can be divided by 3 and produce 2, and 6 can be divided by 2 and produce 3. So in essence, to balance my oxygens, I need to make sure that both of them reach a value of 6. Now, in order to do that, I can just put a 3 in front of the O2, and that will take my oxygens to 6. But the problem is that in the product, if I'm trying to get my oxygens to get to a value of 6, I have to put a 2 in front of the aluminum oxide. And if I do that, my oxygen goes to 6 atoms, and now my oxygens are balanced, but my aluminums went to a value of 4. So when it comes to this, that value of 2 that I started with, I have to erase, and now I have to place a value of 4 before the aluminum. So now, when I count my atoms, that 4 gets multiplied by the subscript of aluminum, and then on both sides of the equation, I have 4 atoms of aluminum and 6 atoms of oxygen. Make sure that you practice with the other problems that we have in this slide.